Math 287, Quest to College. I'm Joe Vasta. This is review 1. So let's work out a few problems that will help us perhaps get ready for the exam. A good thing you might want to do, I might not say this after each problem, is you might want to look at this problem here, pause the video, and see if you can write the answer, and then watch and see what I get. So that's probably a good way of reviewing, is doing that as I do this review. So let's go from 2.1. I believe I did not assign problem number 8, and it asks us to write the matrix with the given elements. Specify the size of the matrix. Your book says specify the dimensions. This is actually a little more appropriate here. Specify the size of the matrix. So it says Aij equals I minus j. And it says I is between 1 and 4 inclusive, and j is between 1 and 4 inclusive. So that would mean that, well, maybe you already know what kind of matrix you're going to have in terms of the size, but you can start off by, like, A11 is going to be 1 minus 1. So A11 is 1 minus 1, which is 0. And then, of course, A12 is 1 minus 2. 1 minus 2 is negative 1. And so I'm not going to write them all down. I'll just say, you know, A13 is going to be 1 minus 3, which is negative 2. And A14 is going to be 1 minus 4, which is negative 3. Okay. A21 is going to be 2 minus 1, which is 1. You'll see a pattern on this. And then 2 minus 2 is 0. And then A23, 2 minus 3 is negative 1. You probably already see the pattern. Look what's happening here. It looks like we have integers, and they are decreasing by 1 as you go across the row. And that's what this thing's going to do. So this one's going to be negative 2. Then here is A13. I said that wrong. Row 3, A31, which is 3 minus 1, which is 2. So I'll go ahead and fill in the rest of this matrix. And you can verify to make sure that I am correct on this. You know, for instance, this is A41, and this is 4 minus 1, which is 3. And then this is A44, which is 4 minus 4, which is 0. So this gives me the answer. This problem here hopefully is not too difficult. It's just getting you to get used to this index notation. So that is problem number 8 from 2.1. Let's do another one from 2.1. This one I just kind of made up because I think I assigned the evens and the odds, so didn't have any left. Give an example of a 4x4 upper triangular matrix A. Okay, so that. Let's go ahead and write. It's another 4x4 matrix here. Oh, sorry, on this last one it says specify the size of the matrix. Size is 4x4. So there it is. Okay, so we have a 4x4 matrix here. It's upper triangular. Upper triangular means all the information is in the upper triangle, which means the lower triangle is going to have all zeros. So it's an upper triangular matrix, which means this. Okay, so that's what upper triangular means. It also says it's not a lower triangular matrix, so I can't just make this the whole zero matrix a 4x4 zero matrix, because this says it's not a lower triangular. It says the trace of this matrix is 12, and A12 plus A21 is 7. Okay, let's do the trace is 12. Well, what is the trace of a matrix? The trace of the matrix is the sum of the main diagonal, and so there's many different answers you can do. I mean, if I just put a 1 there, and a 2 there, and a 3 there, that already adds up to 6. The thing has to add up to 12. So I'm going to need a 6 there. So look, 6 plus 3 plus 2 plus 1 equals 12. Now, this one right here says A12, which is this element here, which we don't have yet, plus A21, which we do have. It's a 0. Those guys add up to 7. So I already have a 0 here, so I guess I need a 7 there. And you can see that 7 plus 0 is 7. Now, as for the rest of this matrix, we're free to put whatever numbers we want. You can make the rest zeros. I'll just make the rest 1s because it didn't stipulate anything on those elements. And what we have here, so we have the answer. And the answer is not unique. So this gives us a little practice in 2.1. We're going to now move our attentions to 2.2. Instead of grabbing a problem from 2.2, I went ahead and went to 2.9, which is a review of Chapter 2, and I'm going to grab problem number 2, which is multiplying two matrices together. So it says compute C transpose B. Now, okay, let's just say, I'll do it in a different color. Let's just say they asked us to compute BC. Well, whenever you do any of these multiplications, you should always do a size check. The size of B is 4 by 2, and the size of C is 4 by 1. So it looks like the inside numbers are not the same. So they ask you to compute BC, which they didn't in problem number 2. You would say undefined. And that, hopefully you saw that in your homework. But that wasn't the problem. The problem that I'm going to do is C transpose B. So expect maybe you might see something like that on the test where it's undefined. I'm going to go ahead and do this one. So C transpose. So I write this column as a row. It's going to be -5, -6, 3, and 1. And then we have B, which is -3, 2, 1, 0, 0 to -3, 1. So hopefully you have paused this video and you have the answer if you're looking at this right now of what this is. And this is just to give you practice multiplying matrices together. We talked about the Roadrunner and the Coyote, and so that is what I'm going to do. I'm going to go ahead and write this out here. Let's see if we can do this actually. This is a 1 by 4. And over here is a 4 by 2. The inside numbers are the same, so I can do this. And the size of the matrix that I'm going to get is going to be a 1 by 2. Okay. Let's go ahead and do this. The Roadrunner and the Coyote. That's what I was saying in an earlier video, so that's 15. I'll write this out actually. Then we have -12. Plus 3, and then plus 0. That's the first entry, and this is going to be a 1 by 2, so there's the first one. And then the second one is going to be 0, -12, -9, plus 1. Okay, let's go ahead and see what we get for our answer here, and it looks like the sun is coming out. I might have to, hopefully it's not, there's some shadows being created by something. Oh, maybe the tripod. I'm going to try to fix this after I do the problem here. So look what I have here. I have 15 minus 12 is 3, 3 plus 3 is 6. And then over here we have -12 and a -9. This gives me a -21. Plus 1 is -20. So there's my 1 by 2 matrix I got by multiplying those things together. Okay, so there's going to be kind of a loud noise here. Okay, and I'm going to go get an oar. It's got a canoe oar right here. Whoa. It just banged the ceiling, so that's always a good thing to do. Bang the ceiling with the oar. And I put it there so it is blocking off the little bit of sunlight so we don't get this weird shadow effect when I put my hand in different places. Let me open up these blinds just a little bit more. Okay. And we'll move on to the next problem. Yeah, as you can see, I'm in a professional studio. Yeah, right. Okay, so that was 2.9 number 2. That is a review of some matrix arithmetic, matrix multiplication right there. Let's go ahead and do the next one, the next even from the review, which is 2.9. I can't get this thing straight here. Number 4. So once again, pause the video, see if you can do this, and I'm going to go ahead and start the problem right now. This is -4 times a, -2, -1, 4, -1, 2, 5, 6, 0. Okay, so -4 times a minus b transpose. Good thing it says b transpose, because if it just said minus b, you wouldn't be able to subtract, because the sizes have to be the same when you add or subtract. So here it goes. I'm going to take the transpose of this. I'm going to write this column as a row, -3, 2, 1, 0, and then this column as the last row, 0, 2, -3, 1. Okay, the order of operations say you're going to want to do that scalar multiplication first, and then we'll do the subtraction. Of course, some of you might be able to just do it all in one thing, but I'm going to go out and write a step here. -4 times each of those 8 numbers. So this gives me 8, because that's -4 times -2, and then we have -16, -8, -24, then we have 4, 4, -20, 0. And then I'm going to subtract this right here. So I'm just writing this same matrix right there. 0, 2, -3, 1. And now I'm going to go ahead and do subtraction. So subtraction, I just look at corresponding elements. 8 minus a -3 gives me 11. And -16 minus 2 is -18. Doing this all without a calculator, by the way. -8 minus 1 is -9. -24 minus 0 is -24. 4 minus 0 is 4. And 4 minus 2 is 2. -20 minus a -3, so that's -20 plus 3 is -17. And then 0 minus 1 is -1. So yeah, just we have to know how to do arithmetic with matrices before linear algebra gets a little bit more complicated. Let's go ahead and do another 2.2 question, which is I'm going to grab it from the review. 2.9, number 10. You have these two matrices, A and B, and it asks me to compute AB. That's the first thing I'm going to do. And then after that, it says determine the values of A and B such that AB equals I2. Okay, first let's compute AB. Okay, so A, B, equals, okay, let's write them out here. Here's A, 1, 2, 3, 2, 5, 7, and B looks like this. 3B, -4A, AB. So what I'm doing is I'm doing that Roadrunner and Coyote thing, but before I do that, let's just check to make sure that this is possible. This is 2 by 3. 2 by 3, and then this one right here is 3 by 2. The inside numbers are the same. My result is going to be a 2 by 2 matrix. So let's see what this 2 by 2 matrix is going to be. The 2 by 2 matrix, we have 3. Let me just write this down. So 3 minus 8. And then this is plus 3a. Okay, the next one's going to be b plus 2a plus 3b plus 3b. Okay, my next one is going to be 6 minus 20. And then we have, okay, so 6 minus 20 plus 7a. And then the last one's going to be 2b plus 5a. And then this is going to be plus 7b. Okay, so compute AB. Well, it looks like we've done that. AB happens to be this guy right here. We're going to simplify things. So the first one's going to be 3a minus 5. This one right here is going to be 2a plus 4b. Down here we're going to have 7a minus 14. And over here we're going to have 5a plus 9b. And then I'll put the parenthesis there. Okay, so we have to do the second part here, and this is part A. I haven't even showed you part B. Gotta go grab some paper here. So the second part asks me to go AB equals I2. So that's what I'm going to do right here. AB equals I2. Okay, and they're trying to have me determine the values of little a and little b such that this will happen. Okay, so AB is, yeah, this is a little redundant in writing this down. The lazy me wants to just set that equal to the identity, but I better just write this down because makes for good videos on YouTube, just this redundancy of math. Everybody's just going to love it. Okay, so we have that right there. There's AB, and I2 looks like this. It's the identity. Okay, so we're trying to find A and B where this will work. We'll just get rid of that. So this gives me 4 equations with 2 unknowns. So I have a 3a minus 5 equals 1. I could actually already solve for a on that one, but I'll write down the other equations. 2a plus 4b equals 0. 7a minus 14 equals 0. And 5a plus 9b equals 1. Now it's possible that the answer to this is there is no such a and b that can make this happen, that can make AB equal I2. Because look, we've got over here we just have single equations with a's. We better hope that we get the same thing here. Okay, so so now I'm getting a little worried here. But why should I be worried? I mean, look, math always makes sense, but you know, like maybe I picked a problem where the answer is it is not possible. So 3a minus 5 equals 1. I'm going to add 5 to both sides, so this would be 3a equals 6, a equals 2. Now if this equation here does not give me a equals 2, then I'm in trouble. 7a equals 14a equals 2. And I suppose I could have just plugged 2 in there to see if it works. So what I have here is, this is good, this is good. I'm going to go ahead and plug that into this equation. 2 times A plus 4B equals 0. So this is 4 plus 4B equals 0. 4B equals negative 4. B equals negative 1. Okay. So I'm going to put a green check mark here because there has been no contradiction yet. Let's see what this one gives me, because now I know, like, A has to be 2 and B has to be negative 1. And if it doesn't work here, then we're going to say that there's no solution. So 5 times 2 plus 9 times negative 1 equals 1. This is 10 minus 9. Did I say negative 1 equals positive 1? 10 minus 9 equals 1. 1 equals 1. This is good to go. So the answer, where, you know, they ask us to determine the values of A and B such that AB equals the identity, we would say A is 2, B is negative 1. Okay, so now what they want us to do for part B is to compute B times A. Okay, and so B happens to be this. So I'll copy down B with the values that we have. So B was 3, and then little b, which we found to be negative 1, negative 4, A, which is 2, and then we have AB, so this is 2, negative 1. That happens to be B. Now if you're thinking, well, Joe, what did you do? What I did is, there's B right there, and then I got these values right there. I plugged A is 2 in, and B is negative 1 in for those, and that's how I got that. And I'm going to multiply this by A, which happens to be 1, 2, 3, 2, 5, 7. And for all you perfectionists out there, I'll go ahead and make A be a color. Okay, there it is. We'll do a size check. 3 by 2 for the first one, and 2 rows by 3 columns for the second one. The inside numbers are the same. And, you know, hopefully you, if you haven't paused the video, maybe pause it and see if you can do this and see if you get the right answer. So it's going to be 3 by 3 and 3 by 3. Let's go ahead and compute this. We have, I'm not going to write it all out this time. I'm going to go 3 minus 2, which is 1. And then 6 minus 5, which is 1. And 9 minus 7, which is 2. Negative 4 plus 4 is 0. Negative 8 plus 10 is 2. Negative 12 plus 14 is 2. Lots of arithmetic here. 2 minus 2 is 0. 4 minus 5 is negative 1. And the last one is 6 minus 7 is negative 1. So you multiply these matrices together and you get this. When you multiply them the other way, A times B, you end up getting I2, the identity. So obviously matrix multiplication is not commutative, which we have mentioned before in the past. Let's go ahead and see if I can find my other pieces of paper that here it is, 2.3. This is what we're going to do. We're going to do a problem from 2.3. 2.3 was the simple, hopefully it was simple for you, where you take a linear system and determine like the coefficient matrix, the right-hand side vector, and the augmented matrix. Now on the exam, it could be the other way around. I could give you some of these things and have you write out the system. So be prepared to go both ways, just like you did in the homework. I just wanted to do one representative problem. Well, how many different variables do I have up here? If you notice, this thing goes all the way up to x5. So, you know, maybe you're making your matrix. There are going to be 3 rows because there's 3 equations, and perhaps you can go like this. Like you could say the first column is x1, x2, x3, x4, x5, and then over here will be the right-hand side vector. This is the constant. Oh, by the way, what am I doing? Gosh, I don't know what I'm doing. For some reason in my head, I was like thinking, let's just write out the augmented matrix. So I'm going to do that part first. Okay, so the first equation says x1 minus x3, or 1x1 minus 1x3, which would mean the rest of these guys right here are zeros, the variables, and then here's your equal sign, and the constant is 7. Okay, let's take a look at the next equation. It says 2x2 plus 3x4. 2x2 plus 3x4. And then all the other variables are missing in that equation, so they're zeroed for their coefficients. And then you have a 0 here for the constant on the right-hand side. And then this third equation says negative 1x1 plus 5x2. There's not an x3 or an x4, so those are zeros. And we have a 4x5. Of course, our right-hand side part is a 1. So this gives me the augmented matrix, which was the third thing they asked for. They said, well, what is the coefficient matrix? I'll go ahead and put the coefficient matrix up here. That's this guy right here. So the coefficient matrix, and this is just me writing, you know, it's just some busy work here. 1, 0, negative 1 for the first column, 0 to 5 for the second column, negative 1, 0, 0, and then we have 0, 3, 0, and then 0, 0, 4, and that gives me the coefficient matrix A, which happens to be this guy. And the other one, the right-hand side vector B, this guy right here. So that's going to be, let's see, B is this column vector 7, 0, 1. Okay, so that's how we do things in 2.3. Now, once again, be prepared to do these kinds of questions, and also the other kind where we give you some of the matrices and ask you to write the system. 2.4. Now, you had a lot of problems like this. I assigned the evens and the odds, and then I couldn't find any of these kinds of problems in the review, but you'll probably get something like this on the test, where you're supposed to classify the matrix as REF, RREF, REF, but not RREF, or neither. So let's just check to make sure this thing is in row echelon form. So the 3 conditions for row echelon form is, the first one is, if there are any rows of zeros, they should be at the bottom. Well, do we have that? Yes, right there. They're at the bottom. Second condition says the first non-zero entry of each non-zero row should be a 1. So there's a 1 there, and then the first non-zero entry here is a 1. Now, if that thing happened to be a negative 1 here, then we'd say it's not REF, and it's not RREF, it would be neither. But look, both of those were 1s, and then everything else is 0 row. The third condition for being REF is, if you have any leading 1s below the first row, they are to the right of the leading 1 in the row above it. And we have that. Okay? There's only 2 leading 1s. So this thing is REF. Okay, so let's check to see if it's reduced row echelon form. The fourth condition says you look at the columns that have the leading 1. So I'm looking at 2 columns. Everywhere else in the column should have zeros. So that first column, yeah, that's good. And then this third column, which has the leading 1, should have zeros everywhere else. Well, it doesn't. There's a negative 1 there. So this is not reduced row echelon form. So if we're trying to classify this matrix, we say, well, it's the second one. REF, but not RREF. Okay, so that's what we were doing in 2.4. Let's go ahead and do another 2.4 question where they give you a matrix and they ask you to reduce it to row echelon form. So I'm actually going to do three things on this problem. We'll reduce A to row echelon form. We'll find the rank of A, and then we'll reduce A to reduced row echelon form. Okay, so now on the exam, that might have one problem where it asks you to reduce to row echelon form, and then maybe the next problem it will give you a different matrix to reduce to reduced row echelon form. So what I want to do is do row operations. My row operations, kind of move over here. I'd like this to be my pivot, so I'm going to go ahead and interchange row 1 and row 2, switch them. So that's not that hard to do. 3, -1, 4, 2, and then 7, -1, 8, 0. Okay, so I'm going to use this 1 as a pivot, and I want to put a 0 where the 3 is. So I'm going to have to multiply row 1 by a -3. So modified row 1 is right below the matrix. -3, +3, -6, -9. And I'm going to go ahead and add that modified row 1 to row 2, and that's going to give me the new row 2. So I'll put it right here. So row 1 is 1, -1, 2, 3. And then the new row 2 is 0. That's what I want. 2. Then we have -2 and -7. Okay, I'm still not done with this. I want to go ahead and use this pivot to put a 0 where the 7 is. So I'm going to multiply row 1 by a -7. Modified row 1 is right here. -7, +7, -14, and a -21. I'm going to add that to row 3. Let's see what my new row 3 is. So 0, and then -1 + 7 is 6. And then we have an 8 minus 14, which gives me a -6. And then this guy right here is 0 minus 21. This is -21. Okay. So there's a few things I can do. I mean, some of you might say, well, maybe you should scale down the row. That would work. I'm just going to go ahead and multiply row 2 by a -3. And I end up getting 0, -6. This is a modified row 2, +6, and +21. And see what happens is when I do that, I end up zeroing out row 3. So row 3 is just this right here. 0, 0, 0, 0. Okay, they want me to reduce A to row echelon form. So this first non-zero entry of row 2 should be a 1. So I'm going to go ahead and scale down that row to 0, 1. I'm multiplying row 2 by 1/2. -1, -7/2. And then the first row does have a leading 1. And so this completes part 1 of this, reduce A to REF. Oh, by the way, row echelon form is not unique, so had you done something different, you could have got a different answer. Find the rank of A. The rank of A happens to be the number of non-zero rows in the row echelon form. So there are 2 non-zero rows here, so the rank of A is 2. Okay, part 3 says reduce A to RREF. So that is what I'm going to do now. Now also note that A does not equal this matrix here. A is row equivalent to it. So A, I'm just going to write it out here, is row equivalent to this. 1, -1, 2, 3. And what I'm going to do is I'm going to multiply row 2 by 2 because I don't like that fraction there. So or, wait, do I want to do that? Nah. Let's just keep it the way it is. There's a reason why I'm keeping it the way it is. So this is not going to require too much work here. To put it in reduced row echelon form, I want to make sure every column that has a leading 1 has zeros everywhere else. And so the first column does have zeros everywhere else, and there's a leading 1 at the top. And then the second column, well, there's a -1 there. Now I want to use this 1 as a pivot to put a 0 there, and all I have to do is go row 1 plus row 2 gives me the new row 1. That's why I was going to change it out, because I didn't want to do fractions, but this is going to be easy enough, I hope. So let's continue this. So my new row 1 is going to be gotten by adding row 1 with row 2. 1, 0, that's what I want there, 0, and then this is going to give me 1, and then I'm going to have 3 minus 7 halves. Well, 3 is really 6 halves. 6 halves minus 7 halves is -1 half. And then row 2, I'm going to keep the way it is. Even if I scaled it up to get rid of the fraction in the end, I'd probably have to, scale it back so there was a 1 there. And so look, here are my leading 1s, my pivots, and in those columns, there's zeros everywhere else. And so this is the answer. They ask me to reduce it to reduced row echelon form. I have that right there. Let's continue. So that was 2.4. 2.5. Was a lot of work when you did your homework because there were a lot of row operations. So 2.5 would say something like use Gaussian elimination to determine the solution. Gaussian elimination says write your augmented matrix, reduce it to row echelon form, and then do back substitution. The Gauss-Jordan elimination is taking the augmented matrix and reducing it to reduced row echelon form, which we're not going to do here. So the first thing I'm going to do is write out the augmented matrix. So the first equation, I have 1, 2, 1, 1, -2, 3. The second equation is 0, 0, 1, 4, -3, 2. And the third equation is 2, 4, -1, -10, 5, and 0. So there's the augmented matrix, which is not in row echelon form. I'm going to use that 1 as a pivot to put a 0 there. So I'm going to multiply row 1 by a -2. So this will give me -2, -4, -2, -2, +4, -6. I'm going to add that to row 3 to get me the new row 3. Okay, so I think I have room to fit it here. So this is 1, 2, 1, 1, -2, 3, and then 0, 0, 1, 4, -3, 2, and then we have 0, 0, -3, -12, so I'm adding those, and then +9, -6. So we need another piece of paper for this. Get another piece of paper. You might notice something, but if you don't notice something about row 2 and row 3, just go ahead and use this as a pivot to put a 0 there. So you need opposites. Put a 3 there. So 0, 0, 3, 12, -9, and +6. What do you notice about this modified row 2 and row 3? Well, it's going to 0 out. And so this is going to get me matrix 1, 2, 1, 1, -2, 3, and then second row is the same. And then the third row is all zeroed out. Now, what you could have noticed is that row 2 and row 3 are multiples of each other. -3 times row 2 is exactly row 3. Well, in any case, it zeroed out row 3. This is row equivalent to my augmented matrix. I have the variables x1, x2, x3, x4, x5, and that's what we had in our original equations. And let's take a look at something else. We also can identify two leading ones, and those leading ones are going to determine that x1 and x3 happen to be bound. Now, the ones that do not have leading ones, those are free, and those are going to be parameters. So let's go ahead and write up the solution here. So x5, it's going to be our first parameter. We'll say it's t. And then x4 is going to be our next parameter, which we need another parameter name, s. And then because x3 has a leading one, I'm going to write out the second equation, which says x3 plus 4x4 minus 3x5 is 2. And that's exactly the equation that we had for our original problem. I'll circle these. And so this really says x3 plus 4s minus 3t equals 2. I'm solving for x3. x3 equals 2 minus 4s plus 3t. And so we have that. x2 is a free variable, so this one we're going to write as, we need another parameter, so I'm reaching back in the alphabet, r. And then the first equation says x1 plus 2x2 plus x3 plus x4. I'm getting this from the first row, minus 2x5 is 3. And that was our first equation in the original problem. So this is x1 plus 2 times x2, so 2r, plus x3. x3 is this guy right here. 2 minus 4s plus 3t, plus x4, so plus s, minus 2x5, so minus 2t. This gives me 3. So solving for x1, we have quite a mess here, because we have oh, so here's a 2 right here. Here's a 2 and a 3, so that's going to be 1. And then we have minus 2r, so I'm kind of skipping a step maybe. And then look at my s's. There's negative 3s on the left-hand side, so it's going to be positive 3s on the right-hand side. And then my t's, look at this, I have 3t minus 2t, which is a positive t on the left-hand side, which means it's going to be a negative t on the right-hand side. And for all the talking I've done and the time I wasted on the video, I should have just written out the step where I combine like terms on the left-hand side. Oh well, my answer is going to be a 5-tuple with x1 first, so this is 1 minus 2r plus 3s minus t. The second part will be r. The third part will be 2 minus 4s plus 3t, comma, and then we have an s, and then a t. And so this right here is the answer. We're not going to be picky on this test, but maybe on the next one we will, where, you know, you have set builder notation, the book writes it a little more formally. But there's the answer to the system that we were given. How many answers does this happen to be? There's infinitely many. Okay, a linear system can have infinitely many solutions, one solution, or no solution. And you'll see that in the next problem here. So let's find the next problem. This one was one of your homework problems, and it's usually asked on the review when I do a face-to-face class. So I might as well just do it since I know it's a problem that's usually asked. And this problem says, determine all values of the constants a and b for which the system has no solution, an infinite number of solutions, a unique solution. So that's what we're going to do. So let's go ahead and write up the augmented matrix for this. So I'll call it A of that. And notice I have two variables and three equations. So the first column is going to say 1, 2, -3. The second column looks like I have some constants a and b. So there's a -a, a +1, and here is a plus b. And the right-hand side vector is 3, 6, 1. 3, 6, 1. Okay, so what I'm going to try to do is put this thing in, well, try to put it in row echelon form. I have some A's and B's, and that is a little confusing there. I'll multiply first row by -2 to try to put a 0 there. So this is -2, +2a, and -2 times a 3 is -6. I'm going to add that to row 2. That becomes the new row 2. Better just use another piece of paper here. Okay. So my matrix here now says 1, -a, 3, and then I have 0. This right here, when you add those, you have 2a plus 1, 2a plus 1, and then the last one is 0, because you have the 6 and the -6. I'm going to go ahead and use this pivot to put a 0 there by multiplying row 1 by a +3. So I end up getting a 3, -3a, and a 9. And so we'll see what that gets me. When I add it to row 3, I end up getting a 0, 3 minus 3, and then here I end up getting a b minus 2a. Okay, because you have a plus b minus 3a, and then here 1 plus 9 is 10. And so that's what I have. Now, I noticed that if I were to add row 2 and 3, I would end up getting rid of the a's. And that's what I'm going to do. So watch this. I'm going to write out row 1. I'm going to keep it the way it is. And row 2, I'm going to keep it the way it is. 0, 2a plus 1. And then I have 0. And then for row 3, I'm going to add row 2 plus row 3, because I can see the two a's will go away, and I'll end up getting 0. And then this would be b plus 1. Okay, and then this part right here is 10. And because, I don't know, I just want to switch row 2 and row 3 around, I'll go ahead and do that. I'll have 1, negative A, 3, 0, B plus 1, 10, and then 0, 2A plus 1, 0. The reason I did that is because I wanted to have the possibility of having all zeros on the bottom row, and I can see a 0 there. I wouldn't be able to have that if I had a 10 there. In fact, that's where I'm going to start off. How could I zero out the bottom row? So let's move this up a little more. Here's the equation. This one was x1. This is x2. Well, I can zero out the bottom row if I end up having a equals what? I mean, this whole thing has to be 0, so if a is negative 1/2. A equals negative 1/2. Now I'm putting it right up here, but I'm focusing on this matrix the whole time. I'm not focusing on any other matrices on this page. So if A equals negative 1/2, then what do I have? Then this thing becomes what? This thing becomes 1, and then negative, in front of a negative 1/2 is a positive 1/2, 3. And then I have 0, B plus 1, 10, and then the last one is all zeros. There's going to be a lot of logic going on here now, so you might want to pay attention to what's happening here with the logic. Here's x1 and x2. Okay, so now I know I have a row of zeros, and I'm looking up here. Okay, so A is negative 1/2. Now, something bad can happen to row 2. It's an equation. You know, it says 0x1 plus this coefficient x2 equals 10. As if this b plus 1 is a 0, because then you would have 0, 0, 10. When can that happen? When b is, so we'll just say if b is negative 1, then second row gives the equation 0 equals 10, which is bad. And so therefore you would have, this would give us no solution. If b does not equal negative 1, then you would have some number here. You know, it could be like 7 or something that is not 0, which then would mean that x2 is bound, because that could be a pivot, you can scale it down, and x1 is also bound. So let's say if b does not equal negative 1, then x1 and x2 are both bound, and therefore we would get one solution. One solution. I know this is, we're going to go ahead and spell this all out at the end. And the last situation, okay, so we've covered all the cases here where A is negative 1/2. If A does not equal negative 1/2, let's see what happens then. Okay. So I need another piece of paper. So A does not equal negative 1/2. You end up getting just this matrix here. You have 1, I'm just going to write it down again. 1, negative A, 3, 0, B plus 1, 10, 0, 2A plus 1, 0. Okay, so if that happens, then this guy right here, let me circle it in green. Then this guy right here is non-zero. Okay? And from the last row, we'll get, so remember this is this way, and this is x1, x2. So from the last row, we have the equation 2a plus 1, that's the coefficient, x2 equals 0, which means that x2 is 0. Well, from the middle row, so we'll just say middle row, you have b plus 1 x2 equals 10. But if x2 equals 0, you end up getting 0 equals 10, which gives you what? No solution. Wow, so there was a lot of logic here, and we're going to try to put it all together now. And so we'll put the answer right here. So they want the case where, what are the values of a and b that will give us no solution? So I'll put that first, no solution. Well, no solution would be, there were two cases when that happened. And one was when a equals -1/2 and b equals -1. So I'll write that down. So this is when a equals -1/2 and b equals -1. But there was another situation we got no solution. It was right here. That was when a does not equal -1/2. So I'm going to put or a does not equal -1/2. So that's no solution. And part B, they want to know when you end up getting one solution. One solution happened when a equals -1/2 and b does not equal -1. So this is when a equals -1/2 and b does not equal -1. And part C was infinite solutions. Well, did we ever get infinite solutions? We did all the cases. A equals -1/2 never gave us infinite solutions. A equals does not equal -1/2 gave us no solution. So infinite solutions, this is not possible for this system. Now, having done this, before you start freaking out, this was the most complicated one that was assigned in your homework. So I did not pick the easiest one, I picked the most complicated one. And what's most complicated about it, it's the logic that we follow to get our answers. And usually in math classes in high school and even in some of the lower ones in college, we're not really trained to do logic. And we should, because math is built on logic. So that could have probably been one of the hardest problems that we would see in this review. Make sure you know how to do problems like this. We're going to go ahead and continue our way through Chapter 2. Our next Chapter 2 problem is this one right here. So go ahead, pause the video, see if you can find A inverse, or find the inverse A inverse. Okay. So to find the inverse of this, I would highly suggest with 2x2 matrices that you do the shortcut that we derived in Chapter 3. The inverse of this matrix equals 1 over the determinant. The determinant of this matrix is AD minus BC. So this is 20 minus a -14, or 20 plus 14, which gives me 34. So I am doing the shortcut. If you're thinking, what shortcut are you doing? I'll go ahead and show you the shortcut. A, B, C, D. A inverse is 1 over the determinant of A. And then in here, this is just memorization. Switch your D and A and negate your B and C. Okay, so that's the formula I'm using. Now for a 3 by 3 inverse, you have to do it a longer way. Okay, so I'm going to switch my D and A. So 5 goes here and a 4 goes there. And negate my B and C. So -7 and a negative in front of the -2 is a +2. Now for this test, this is not acceptable when I ask you to find the inverse matrix. We want to actually write this as a 2 by 2 matrix. And when we do, we end up getting 5 over 34. Yeah, there's some fractions in here. -7 over 34. 2 over 34, which reduces to 1 over 17. And then 4 over 34, which reduces to 2 over 17. And so there is the answer. The inverse matrix is the matrix that you would multiply by the original, and it doesn't matter which way you multiply it, on the left or on the right, it would give you the identity. So there's the answer to that. Let's go ahead and do another 2.6 problem. Find the inverse of this 3 by 3 matrix. So we can't do the shortcut. Now, are there other ways of finding the inverse of a matrix? Yes. Are they simpler than the one I'm going to do? Some of them are a little tougher. Okay, so I try to pick the simplest one. And so what we're going to do is the Gauss-Jordan Technique to find the inverse of a 3 by 3 matrix. We could have used the Gauss-Jordan Technique on the last problem, but it would have taken us like a lot longer to do. We have a nice shortcut for 2 by 2s. So here it goes. The Gauss-Jordan Technique says you write this matrix you go like this, and then you go ahead and you put the identity right here. So this is a super augmented matrix in the sense that you are solving 3 equations and 3 unknowns at the same time, but you don't even have to think about that. What you're going to try to do is you're going to do row operations to turn these 9 numbers into the identity, and then when you have completed that, you'll see the inverse matrix right there. Now, it's possible that you cannot turn these 9 numbers into the identity. It's possible you get a row of zeros here, just right here on this, which means that A would then be non-invertible. Okay, so let's see what we have here. So this is going to be quite a long process using row operations. I'm going to go ahead and switch row 1 and row 2. Okay, so here it goes. I've got this 3 by 6 matrix. 1, 4, 2, 0, 1, 0, and then -2. I can't even do this. Let's see if I have some white behind here. Okay, so -2, -3, 1, 1, 0, 0, and then the last one I'll keep like this. 0, 5, 3, 0, 0, 1. Okay, I'm going to use this 1 as a pivot to put a 0 there. I've got a 0 there, so that's a bonus. I'm going to multiply row 1 by 2. It's going to give me 2, 8, 4, 0, 2, 0. I'm going to add that to row 2 to give me the new row 2. I'm also going to need some more paper here. And so what will I have? This gives me, okay, so 1, 4, 2, 0, 1, 0. And then here we're going to get 0, 5, 5, 1, 2, 0. And then we'll copy the row 3 down. So we have that there. 0, 0, 1. Okay, so now that pivot has served its purpose. Now I'm going to use this right here as a pivot. I'm just going to go row 2 minus row 3 gives me the new row 3. And so I'm going to go ahead and write out row 1 the way it is, row 2 the way it is, and row 3 I'm going to go row 2 minus row 3. So 0 minus 0 is 0. 5 minus 5 is 0. 5 minus 3 is 2. 1 minus 0 is 1. 2 minus 0 is 2. And 0 minus 1 is negative 1. Okay, so I had to put this matrix on the right-hand side into reduced row echelon form, or this whole matrix, and so it looks like it's going to be invertible. I'm now going to use this 2 as a pivot to make that 5 a 0. Now your book would scale this down, so this would be a 1/5 and a 2/5. I don't want to do that yet. I'm going to multiply row 2 by 2 and multiply row 3 by 5. Oh, that's not going to put opposites there, so I want opposites. To get opposites, let's make this a negative down there. Okay, so row 2 times 2 is going to be 0, 10, 10, 2, 4, 0. Row 3 times negative 5 is going to be 0, 0, negative 10, that's what we want opposites there. And then we have negative 5, negative 10, positive 5. I'm going to add these guys together, and that's going to get me the new row 2, thus putting a 0 there. I'm also not going to write row 1 yet for an obvious reason here. So here is row 3, which is 0, 0, 2, 1, 2, negative 1. Okay, row 2 is going to be 0 plus 0. And then we have 0 plus 10. And we have negative 10 and a 10. That's what we wanted, a 0 there. And then we have a negative 5 plus a 2 is negative 3. Negative 10 plus 4 is negative 6. 5 plus 0 is 5. The reason I waited on row 1 is I am still using, where is my orange pen? I'm still using this as a pivot. So what I'm going to do now is I'm going to go ahead and go row 3 minus row 1 gives me the new row 1. No, let's do that the other way. Row 1 minus row 3 gives me the new row 1. So row 1 minus row 3. So this is 1 minus 0 is 1. 4 minus 0 is 4. 2 minus 2, this is what we want, 0. 0 minus 1 is negative 1. 1 minus 2 is negative 1. 0 minus a negative 1 is a positive 1. Okay, so this is good. I can't scale down any of the rows. I'm going to use the 10 as a pivot. As much as your book discourages me from doing this, I don't care what your book says, actually, because I don't want to do fractions. I'm going to put a 4 there, so that's going to put a 40 there, and a 10 times the first row, which will put a 40 on top. And what do I want to do with this? I want to go... It doesn't really matter which one gets the negative. I'll put the negative on the bottom, so I'll have a 40 up there and a negative 40 there. So row 1 times 10 is 10, 40, 0, negative 10, negative 10, and a positive 10. Row 2 times negative 4 is 0, negative 40, 0, 12, 24, and negative 20. I'm going to add those together, and that's going to give me the new row 1, new piece of paper. And so, what do we have? We have the new row 1 is 10, 0, 0, 2, this is 14, negative 10. And then row 2 and row 3 I'm going to leave alone. So this is 0, 10, 0, negative 3, negative 6, 5, and then we leave row 3 alone as well. So 0, 0, 2, 1, 2, negative 1. Okay, is this matrix in reduced row echelon form? Almost. We just have to put a 1 there, a 1 there, and a 1 there. So I'm going to multiply row 1 by a 1/10, multiply row 2 by a 1/10, and multiply row 3 by a 1/2. And that should get me what I want. So row 1 becomes 1, 0, 0, 1/5. Okay, it's 2 times 1/10 is 1/5. 14 times 1/10, or 14 over 10 is 7/5. And then negative 10 times 1/10 is negative 1. Okay, row 2, it's going to be 0, 1, 0. Then we have negative 3/10 and negative 6/10, which is actually going to be negative 3/5. And then 5 over 10 is 1/2. Row 3 times 1/2. So 0, 0, 1. And you see the identity right there. That's what we're after. Let's put a line there. And then I have 1/2, which is 1/2 times 1. And 1/2 times 2 is 1. And 1/2 times negative 1 is negative 1/2. Woo! So our final answer then is this. And I know this is a little redundant, but here's A. A happens to be negative 2, negative 3. There's a reason I'm doing this. 1, and then 1, 4, 2, and 0, 5, 3. Oh, when you do your test, you should be showing all your work. If I just see the answers, I really can't give too much credit for that. So you have to show your work that you're doing. So here is A inverse. This is what we're looking for. It is this matrix right here. And so let me write out that matrix. That matrix is 1/5, 7/5, negative 1, negative 3/10, negative 3/5, 1/2, 1/2, 1, negative 1/2. So there's the answer. Lots of row operations, and that's what's probably been annoying some of you when you've been doing your homework. My next question is this one right here. Use A inverse to solve the system. Now, what do we know about this system here? This system has the same coefficients as, or has the same coefficient matrix as this. So I wanted to save us some time, and on the test I might do the same thing. I might have you use A inverse, maybe give you what the inverse is, or have you work off another problem. And so basically we have the problem that looks like this. It looks like AX equals B, where A equals the coefficients there. Look, negative 2, negative 3, 1, and then this one is 1, 4, 2, 1, 4, 2, and then 0, 5, 3. So this is, if you didn't understand why I put this back here, is because that's exactly this matrix here. The right-hand side vector B happens to be these three numbers here. So 1, negative 1, 0. Okay, when I solve AX equals B, using A inverse, I'm going to multiply both sides of this equation on the left on each side by A inverse. So look at this. A inverse A times X equals A inverse times B. Well, this right here, A inverse times A, is the identity, which is kind of like 1. 1 times that is going to be what I'm looking for. There's the solution. Vector X is going to be A inverse times B. Well, from the last problem, we figured out what A inverse is. It's this guy right here with all the fractions. So let's write that up. This is 1/5, 7/5, negative 1, negative 3/10. So we did all the work already on this. Then we have 1/2, 1, and negative 1/2. And so all I really have to do is multiply that by the right-hand side vector B. So let's get rid of this because now we know what A inverse is from the last problem. So we have, let's see, 1, negative 1, 0. And so solving this system is just doing matrix multiplication. And look at this. This is 1/2 minus, oh, that's not 1/2, is it? It's 1/5 minus 7/5, which is negative 6/5. And then what do we have here? We have, and then there's a 0 there, so we're not going to count that. And then this is negative 3/10 plus 3/5, or it's really plus 6/10. So negative 3/10 plus 6/10 is 3/10. Just doing some fractions here in my head. And then we have a 1/2 minus 1, and then there's a 0, so this is going to be negative 1/2. Now you could write your answer like that, or you could write your answer like this: negative 6/5, 3/10, negative 1/2. And we've just solved that system by using matrices. Now normally what I would do, if I just had a system from scratch, I would just do Gaussian elimination, but on the test, if asked to do it this way, you should multiply the inverse matrix times the right-hand side vector. This way will only work if you've got an n by n system. That means n equations and n unknowns, and this matrix here that you have right here has to be invertible, otherwise this is not going to work. Well, we got one more topic to cover, and we'll do that with 2 problems. So this is chapter 3, which happens to be the determinants of square matrices. So let's get into chapter 3. 3.5, I think, is the review. Maybe it's not. I think it's the review. And so what do we have here? We have A and B are 4x4 matrices. The determinant of A is negative 2, determinant B is 3. Compute determinant of this. Okay, so this is to see if we know our properties of determinants. So I have the determinant of a product. So here's a matrix and here's a matrix. It's really the product of the determinants. And so that's the first thing to realize. So this is really determinant A inverse B transpose. And then this is times the determinant of 2B inverse. Okay, now the determinant of like a matrix C transpose, we just use the letter C, is the same as the determinant of matrix C. So for this one, I can say this is really determinant. We don't have to put the transpose there. This is A inverse B. And then over here, we're going to have to use that property where there's a scalar. So this is going to be the scalar. Now, a lot of people do this. They go scalar times the determinant of B inverse. But that's not really what it is. It's going to be the scalar raised to a power. The power comes from this. So it's 4x4, so it's 2 to the 4th power. Okay, looks like we have another product here. So this is determinant A inverse, determinant B. We have 2 to the 4th, which is 16. And then we have determinant B inverse. Okay, determinant A inverse, if you remember that property, it's going to be the reciprocal. So it's actually going to be negative 1/2. Determinant B, well, it's just right there. That is just 3. And then we have a 16 here. And then we have determinant B inverse, which is the reciprocal. So this is 1/3. The 3 and the 1/3 become 1 when you multiply them. And then you have 16 times negative 1/2. This is going to give you a negative 8. Okay, so that's properties of determinants. Let's go ahead and do one more problem where we are to find the determinant of a matrix. Now I believe 3.5 number 29 asks some other things, but this is the important part that you have to know for the test. So how do I find the determinant of a matrix? Well, I'm going to try to choose a row or column that has the most zeros. And so, you know what, just to make it interesting, I'm going to go like this. Okay, so to find the determinant, here's the other notation for determinant, which is more compact than the last problem. I'm going to go ahead and put this 1 here, and then a 0, and then a 0, and then the 5. Now I got to remember the plus minus configuration. You might have remembered this is what we did when we were doing determinants. And it has to do with cofactors and things like that. So it looks like a chessboard. And we see that this 1 is in the negative position. There's always a plus in the top left corner. So that's in the negative position. And then this is plus, minus, plus. And now I'm going to go ahead and figure out it's called the minor of this element 1 here. And it's going to be the determinant of the matrix that is gotten by crossing out the row and column that contains that 1. So this is going to be negative 3, 2, 2, 1, 1, 1, 2, 3, negative 4. Now this one has a minor as well, gotten by crossing out the row and column that contains that 0, but it's just going to be multiplied by 0, so we don't really even care. We're not going to even write it down, and same with this 0. That's why we pick a row that has a lot of zeros in it. And now the minor of 5 is going to be this. So I'm going to cross out the row and the column that has that 5. We have 0, negative 3, 2, 0, 1, 1, 1, 2, 3. So now this determinant of this 4x4 matrix breaks up into little problems where you're finding determinants of 3x3 matrices. Okay, we'll continue on this. Determinant A is negative 1. We'll just keep that negative 1 there. And now I have to find the determinant of this matrix. To find the determinant of this matrix, I'm going to travel across the first row. Okay, someone's using a leaf blower outside. That's good to know. Let's go ahead and put a bracket here. I have negative 3, 2, and 2. Okay, the negative 3 is in the positive position, so I'll put a little plus in front of there, and then this 2 is in the negative position, and this 2 is in the positive position. And then we just draw a new plus and minus checkerboard for this one. We don't use, negative 3 here was in the negative position, but over here it's in the positive position, so plus, minus, plus. And now I'm going to go ahead and figure out the minor of negative 3, which is going to be negative 4 minus 3, which is negative 7. Okay, that's the determinant of 1, 1, 3, negative 4. And then the next one happens to be I cross out the row in the column that contains that 2. I have 1, 1, 2, negative 4. So this is negative 4 AD minus BC. Negative 4 minus 2 is negative 6. And then I cross out the row and column that has that 2, and I get 1, 1, 2, 3. And that determinant would be 3 minus 2, which is 1. Okay, meanwhile over here we have a 5, and I definitely want to travel down this column here. And so the 1 is that an arrow, or I don't know what that is, but it's getting messed up. So the 1 is in the positive position, and I'm going to go ahead and figure out the minor of that, which is negative, determinant of negative 3, 2, 1, 1. So this is negative 3 minus 2, which is negative 5. Okay. So now, what do we have? We have negative 1. This is just doing some arithmetic now. So this is 21. That's a negative 3 times a negative 7. Plus 12 plus 2. And then this is 5 times a negative 5. So what do we have here? We have negative 1 times, we got to add this up, so this is 33, 34, 35, 35, and then we have minus 25. So this gives me negative 35 minus 25. And you add those together, you end up getting negative 60 for the determinant of that 4x4 matrix. And that completes the review. Study hard. Have a good day. I'll see you in the next video.